Welcome back, everybody. We are to the last chapter and the second to last video. We're going to do chapter 11, and we're going to focus on a goodness of fit for this video. And a goodness of fit test is used to see if proportions of the categories of the qualitative variable fit a certain distribution. Basically, what we're saying is if we have a scenario where we can observe data and then we can say what theoretically should be true. So, for example, flipping a coin, theoretically it should be 50% are heads, but the observed may not match that. And so what we want to say is our observed data close to our expected data? So let's get started. So here we go. All right, so if a die is rolled many times, the die should land on each number about 1/6 of the time. And we are going to ask the question, is this going to fit our data? Does the dice fit this claim? So let's say that we were flipping or rolling this die. We'll just make this up. We'll say n is 60 just to keep it nice and simple. Our expected is going to be E equals N times P. P in this case is the 1/6. And if we're going to talk about our expected, rolling a 1, 2, 3, a 4, a 5, or a 6, what we would expect is 60 times 1/6, or rolling a 1 10 times, rolling a 2 10 times, rolling a 3 10 times, 4 10 times. Each one we should be rolling about 10 times. This is what we expect with a fair die. Now, in reality, it doesn't actually turn out that way. So what we're going to have is, let's set up another table. And rolling a 1, a 2, a 3, 4, a 5, or a 6. And I'm just gathering this data from a different data set. This is not written anywhere on this paper. So we'll say 13, 9, 12, 14, 6, and 6. So this is the observed. And the big question is, does it fit? Meaning, does this fit with our observed data? And that's what a goodness of fit test is. This is what we expect to get and what we have actually observed. Is it a good fit? So let's talk about what our null hypothesis is going to look like. All right, so start with the assumption that the proportions of your experiment do follow a certain distribution. So we're going to assume that that there is a good fit. And then we'll have to analyze that. So the proportions do follow the claims distribution. Versus the proportions do not follow the claims distribution. And when we get to a specific scenario, we'll get more specific. Calculate the number of data points we should get in each category if the distribution is a good fit. So the expected count is going to be the N times P. Collect data and count how many times we observe each category. So we're going to have both an observed set of data as well as an expected amount of data. And then we're going to do a comparison. And our conclusion is going to be, if there's a big difference between what we expect and what we observe, we're going to reject the null hypothesis. meaning it's not a good fit. And if there isn't a big difference, then we're going to fail to reject. And because we're looking for a big difference, we're always running a right-tailed test. Meaning in our chi-squared distribution, you're always going to have a right-tailed test. And that's going to follow for us. All right, let's get into some specific examples. Conduct a goodness of fit. Data needs to be randomly selected. The sample data consists of frequency counts for each of the different categories. And for each category, the expected frequency is at least 5. That's fine. All right, our null hypothesis, the frequency counts agree with the claimed distribution, or the frequency counts do not agree with the distribution. Here is our big deal. Here is our test statistic. And to be clear, our degrees of freedom are k minus 1. And I'll define here what k is in just a moment. So once again, k minus 1 is the degrees of freedom. And just to reemphasize, we are always right-tailed. O is going to represent the observed frequency of an outcome. Oops. E is going to be the expected. And that's what you see in the formula there in the yellow. K is going to represent the number of categories, and N is going to be the total number of observed values. And let us move on, get to a specific example. Here we go. Records of randomly selected births were obtained and categorized according to the day of the week that they occurred. Because babies are unfamiliar with our schedule of weekdays, it's reasonable claim that births occur on different days with different frequency. And we're going to test that at the 1% level. All right. So let's just interpret this table here for a moment. We're saying that on a Sunday, there were 77 births. On a Monday, there were 110. On Tuesday, there were 124, and so on. Now, we are going to apply the same proportion to each day of the week, meaning the day of the week is irrelevant to what we would expect as far as number of counts per day. So let's start with our null hypothesis. Births do not occur on different days with different frequency. Versus births do occur. And different frequency. All right. So before we do anything, I want to point out that K in this case is the number of days of the week, which is 7, which means our degrees of freedom is 6. Now I need to calculate N. So let's add up all of the number of births. So 77 plus 110 plus 124 plus 122 plus 120 plus 123 plus 97. So I'm getting that N is 773. Now the proportion is 1 and 7, is what we're going to expect. So our expected value is going to be 773 divided by 7. Now, I need to emphasize some calculators need this level of precision, so I'm not going to round this off. I'm going to store this. So if you look at my calculator, at the bottom left, third button up, it says STO. So I'm going to hit STO. It's going to take that answer 110.42857 and so on. It's going to store all of those digits. And if you look above, see where it says alpha, the green, right below it, there's a little green A above the math button. I'm going to access that by hitting the alpha button and then the A, and then hit enter. And what I've done is I've stored that number with all those digits in it, so there's very little round off error, into memory an A. And here's the reason I'm doing this. I'm going to go to commercial. Let's see. Okay. So you'll notice that in list 1, I have my Sunday is 77, then 110, 124, and so on. So there's my list 1. My list 2 is going to be my expected. And instead of typing in 10.42 and so on, I'm going to hit alpha A and just hit enter. Alpha A, enter, alpha A, enter, alpha A, enter. And what that's going to do is that's going to minimize the round off error as I filled in my expected category. So my observed is in list 1, my expected is in list 2. And the test that we are going to run is a chi-squared goodness of fit test. And let's go find that. I want to point out that the reason I have this table here is because this is going to be the 10.43 that's rounded off, and then I would subtract the 2. I put that value there, and this here is going to get me my test statistic. If you remember, that's that there. But the good news is the calculator does all this work for us. So let's go to goodness of fit test. So stat tests. It's going to be way down towards the bottom. Chi-squared goodness of fit test. Now I want to point out, if you have a TI-83, like an older calculator, it may not have that goodness of fit test, and you may have to do this by hand. Hopefully we all have newer calculators or are using this free calculator. So the observed is in list 1, expected is in list 2. The degrees of freedom in this case is 6. And let us, this calculator is a little weird. So we're going to get our test statistic. So our test statistic is chi-squared equals 16.895, and our p-value 0.00967. And I want to point out that that is definitely a little bit less than my alpha, which is 0.01. Let's find our alpha. There's our alpha there. And because our p-value is less than our alpha, we are going to reject the null hypothesis. Which means there is enough evidence to support the claim that births occur on different days with different frequency. Now, what does all that mean? That means that somehow different days of the week are going to have more, and other days of the week are going to have less births, which is weird. And it looks, just based on the data that we see here, it looks like the weekends have fewer births, and days during the week have more births, peaking out on Tuesdays for whatever reason. So all we can conclude from this is that it appears, based on this data, that the frequency of births is different depending on the day of the week. Now, the big question would be, why is that so? Which we're not going to answer in this class, unfortunately. All right, let's talk truck colors. In a recent year, the most popular colors for light trucks were white at 30%, black 17%, red 14%, silver 12%, gray 11%, blue 8%, and other 8%. Here we have our observed data, which for me is going to be in list 3. You can erase your list 1 and clear that out and put that in there. Now, let's, first of all, there are 1, 2, 3, 4, 5, 6, 7 categories. So K is 7 in this case, which means my degrees of freedom is 6. We now need to find N. So let's take a moment and add up all of the number of trucks. So 42 plus 31 plus 31 plus 29, 23, 17, and 7. So I'm getting 180 is my N. Now our expected is going to be the 30% times 180. That's for the black. I'm sorry, that's for the white. Then 17% of 180 is going to be the black, and so on. But here's what I'm going to do. I'm going to go directly to my list. And you'll note I have in my list 3, 42, 31, and so on. So I have the data. For our expected, here's what I'm going to do. I'm going to directly type in 0.3 times 180. Then I'm going to go 0.17 times 180. And you'll notice I'm doing the computation directly into the list. You don't have to, you can do it separately and write it out, that's fine. So 0.14 times 180. 0.12 times 180. 0.11 times 180. 0.08 times 180. 0.08 times 180. So there are my expected values. And you'll notice there's a different proportion for each of the different categories. So in the previous one, they were the same proportion. In this one, they're all different. Okay, and we are looking at our alpha being at 10%. So let's look at our alternative, our null hypothesis. The proportion of colors of light trucks is distributed as follows. And we have our percents there. And our choice, by the way, this is not the claim. The distribution is not the same as the stated null hypothesis. That is the claim. All right, so let's draw our picture, which we didn't need to do for the previous one, but this is asking for this. And again, this is a right tail test. Remember, this is at 10%. And we need our, we need our table and formulas for this one. And we need our chi-squared distribution. There it is. Remember, this area to the right, so it's 0.10. So let us highlight what we have here. So 0.10 is here. Degrees of freedom is 6. So we are looking at 10.645 is what I'm seeing. So 10.645, that is our critical value. And we are going to need to find our test statistic. Once again, we're going to be running a chi-squared goodness of fit test. So we'll go to stat, tests, scroll down, goodness of fit test. And my observed is no longer in list 1, I'm in list 3. And my expected is in list 4. Degrees of freedom happens to be the same in this case. And our test statistic is 11.331. That's our chi-squared. And we need to check to see where that is. And that's looking to me like we are definitely in the critical region. We are beyond the 10, we're about there. Which means in this particular case, we're going to reject the null hypothesis. So reject null hypothesis. Which means there is enough evidence to reject the null hypothesis. It can be concluded that the percentages of light truck colors are significantly different from those given in the null hypothesis. So meaning our expected is not matching our actual observed data in this case. And that is the goodness of fit. Hope that helped.